Hi everyone, and welcome to AP Chemistry Review. It's me, Dr. V, and today we're going to talk about free response question number 1 from the 2025 exam. Now, as you're getting ready to take the AP exam, I want to remind you it is going to be a hybrid exam. The multiple choice questions will all be online using the Blue Book app, and the free response questions will be presented to you online in the Blue Book app, but you're actually going to record your responses on paper in a paper answer book. While you're taking the exam, you will have a paper periodic table and a reference sheet for the entire exam, and those will both be available to you digitally as well. You'll have access to the online Desmos graphing and scientific calculators. That's a change from last year where you only had the graphing calculator. And you'll also be able to use your handheld calculator throughout the entire exam. As we get started, let's talk about free response question number 1. It's one of the long free response questions, and that means it's scored out of 10 points. It is a kitchen sink question. You'll see that as we go through it. It covers a variety of topics. You will want to make sure before we go any further that you have your calculator and your periodic table and your formula sheet. What I want you to do is listen to me present each part of the problem and then pause the webcast and try to answer it yourself. Right? I want you to use this as a learning opportunity and to find out how much you can do on your own. It is very important that you show your work and your setup for any calculations. After you've tried to answer it on your own, I want you to score your work, listen to my explanation, and decide if you earned the point or not. Remember, there aren't any half points. Either you earn the point or you don't. So let's jump right in. An incomplete mass spectrum for magnesium is shown in the diagram. The percent abundance of magnesium-24 is 79%. The percent abundances of the other two natural isotopes of magnesium, magnesium-25 and magnesium-26, are approximately equal. So the question is, complete the mass spectrum in this part by drawing thick lines in the appropriate locations to represent the percent abundance of magnesium-25 and magnesium-26. Now we're told that these two are approximately equal. The heights of the lines of the graphs that we draw should be the same height. So 79% is what we know. There's two of them. They're equal. Let's set that to be equal to x. That's going to add up to 100. So when we solve for x, we get 10.5%. And so we need to draw lines at 25 and 26 that go up to 10.5. Now, of course, the graphs are only marked off every 10, so this can get a little bit tricky. So we do need to have two lines that are the same height. They need to be between 10 and 11. If they're too high, you're not going to get credit. If they're not the same height, you're not going to get credit. And that's what you needed to draw for 1 point. It's really the graph that is the key here. So if you did the calculation correctly, but then drew your lines unevenly, or they went up to, in some cases, they went up to 50%. We had lines going up to 80%. The graph is what's important. So if you had the calculation correct, but your graph is not, you are not going to earn the point here. Now, the question goes on and says, describe the difference in atomic structure that accounts for the difference in mass between magnesium-25 and magnesium-26. And the bulk of what you need to be talking about here is neutrons. The two isotopes have different numbers of neutrons, and that's really all you had to say. There are a couple of ways you could have written alternative answers. You could have said magnesium-26 has one more neutron than magnesium-25. You could have said that magnesium-25 has 13 neutrons and magnesium-26 has 14 neutrons. Any of these would be okay. If you talk about protons or electrons, you don't get any credit. The other thing is that if you did talk about the numbers of neutrons for magnesium-25 and for magnesium-26, you had to have the correct number of neutrons. And that's what you needed to talk about to earn 1 point for A Part 2. Part B continues. The particle diagram shown represents a magnesium ion, Mg2+, in beaker 1. A sodium ion, Na+, in beaker 2 has a weaker attraction to water than the magnesium ion does. So we've got a magnesium ion here. The close-up is a magnesium ion surrounded by 4 water molecules, and you'll notice the oxygen portion of the water molecules is closer to the cation. Explain this phenomenon using Coulomb's law in each of the following. So here we're going to talk about the relative charge of the ions. The key point that you need to make in your answer is the charge of the magnesium ion, which is 2+, is greater than the charge of the sodium ion, which is 1+. Because of that greater charge magnitude, we're going to end up with stronger Coulombic attractions between the cation and the oxygen atom of water, which has a partial negative charge. You don't want to say that it's an oxide ion here. It's a partially negative oxygen atom in the water molecule. One thing I really want to emphasize here is that you needed to compare the ion charges. Just restating them isn't enough. You had to say that the magnesium ion's charge was greater than the charge of the sodium ion or vice versa. And that's what you needed to say to earn the point here. Now, B Part 2 was quite tricky, and it was actually, I think, written to be tricky to earn the point for part 2. Explain it using the relative radii of the ions. A lot of students misinterpreted this, I think. The magnesium ion has a smaller ionic radius than the sodium ion. We don't really need to go into why here. We just need to state that comparison, right? They both have the same number of occupied energy levels, but the magnesium ion has a stronger nuclear charge because it's got more protons, and so it's going to hold them in more tightly. So we don't actually have to explain that here. This means that the distance between the magnesium ion and the oxygen atom in water is shorter than the distance between the sodium ion and the oxygen atom in water. And because the distance between magnesium ion and oxygen is shorter, as that interparticle distance decreases, the Coulombic attraction between the ion and the water molecule increases. That's why the attraction for magnesium to water is stronger than the attraction from sodium ion to water. And that's what you needed to say to earn the 1 point. You had to compare the radii correctly and talk about the shorter distance between the ion and the oxygen atom in the water molecule, and that's going to give a stronger attraction. You need to make sure that you are comparing the interparticle distance, the center of the cation, to the center of the oxygen atom. It's not the attraction between the nucleus and the outermost electron of the ion. It's not that kind of attraction. You want to make sure when you're answering Coulomb's law questions that you talk about what particles are actually interacting here. Part C says, calculate the pH of the solution in beaker 2. Well, the solution in beaker 2 is a sodium hydroxide solution, and we know that sodium hydroxide is a strong base. And so essentially what we're told here in the diagram is that the hydroxide ion concentration is 2.80 times 10 to the minus 4th molar. So we're given the hydroxide ion concentration, and we need to find the pH. Well, if we take the negative log of the hydroxide ion concentration, we get the pOH. So if we take the negative log of 2.8 times 10 to the minus 4, we get a pOH of 3.553. I do want to point out that the hydroxide ion concentration as given to us has 3 sig figs. And so a pH or a pOH value based on this should have 3 digits after the decimal point. So a pOH of 3.553 actually has 3 sig figs. It's not 4, it's 3. And if you don't know that, well, I wanted to point that out to you. This question was not scored on sig figs, but you still want to know these details because it's what good chemistry students know. One of the common things you want to watch for is stopping too soon. You can't do this calculation in one step. There are 2 parts to the calculation. If you stop here, which many students did, you're really just reporting a pOH. So I did it by using the relationship pH plus pOH equals 14. So if I subtract my pOH from 14, I get a pH of 10.447. And that's what you needed to do to earn 1 point. Now, there are alternate paths through this problem. I could have used my KW expression to find the H plus concentration and then take the negative log of the H plus concentration. I'm still going to end up with an answer of 10.447. There can be more than one way through a problem, and that's fine. You just want to make sure you answer the problem thoroughly. Part D says, a student combines 35.00 milliliters of 1.85 times 10 to the minus 3rd molar magnesium nitrate with 50.00 milliliters of 2.80 times 10 to the minus 4th molar NaOH, as shown in the diagram. Calculate the magnesium ion concentration after the 2 solutions are combined, but before any reaction takes place. And then in parentheses it says, assume that the volumes are additive. So if we look at the diagram, beaker 1 has 35.00 milliliters of the 1.85 times 10 to the minus 3rd molar magnesium nitrate. It's really the magnesium ion that we care about here. And beaker 2 has 50.00 milliliters of 2.80 times 10 to the minus 4th molar sodium hydroxide. And it's really the hydroxide ion that we care about here. The other ions are spectators. And the implication is that we're pouring them both into beaker 3 and they're going to combine there. Well, we're already told to assume that the volumes are additive, so we need to know the total volume. That's a pretty good clue there. So the total volume is the 35 mils from the magnesium solution and the 50 mils from the hydroxide solution for a total of 85.00 milliliters. And the equation we need to use in order to answer this question is the old standby of M1V1 equals M2V2. And again, we're all interested in the magnesium ion concentration, so we're interested in the beaker 1. You can rearrange that to solve for a molarity. So M2 equals M1V1 over V2, because the moles that are present of the magnesium ion aren't going to change before and after. It's the volume that's changing. And we're going to use our V total as V2. And if you don't know this equation, it's really handy. You should make sure you add it to your toolkit. So we're going to use the 85.00 milliliters as V2. M1 is the molarity of the original solution in beaker 1, and the volume was the original volume of the solution in beaker 1. So I'm going to substitute those in. All right, so the molarity times the volume divided by the new total volume gives me a molarity of 7.62 times 10 to the minus 4th molar for that magnesium ion concentration. That's what you needed to do for 1 point. Now, it's a fairly easy calculation to do, and this is a very common type of problem for dilutions, one you should definitely be able to do, but students did often make mistakes. Common errors include putting the wrong volume and concentration together, so using the volume of beaker 1 with the molarity from beaker 2, or vice versa, things like that. Solving for the sodium hydroxide new concentration, not using the total volume, things like that. So you want to pay attention and make sure you're using the right numbers. You were given all the information you needed here. And then it goes on to part E. The dissolution of magnesium hydroxide is represented by the following equation. So we have solid magnesium hydroxide on the left to establish an equilibrium with magnesium ions and 2 hydroxide ions, and we're given a value of KSP of 5.61 times 10 to the minus 12. Like most KSP values, a very tiny little number. And we're asked to write the expression for the solubility product KSP. We do have the balanced equation, and so writing an equilibrium constant expression from that is reasonably straightforward. So we write KSP equals magnesium ion concentration times hydroxide ion concentration squared. And that's what you needed to write to earn the point for E part 1. Checklist. Make sure you're writing these correctly. It had to be square brackets. If you wrote parentheses, you don't get credit. You needed to show both ion charges. It's not magnesium metal, it's magnesium 2 plus ion. Right, the ion charges are important. It's hydroxide ion, not OH. You need to leave out the solid. We don't put solids in KEQ expressions of any type. So the solid needs to be left out completely. And we needed to make sure we have an exponent of 2 for the hydroxide ion concentration, right? Hydroxide had a coefficient of 2 in the balanced equation. We need to square its concentration in the KSP expression. All those things need to be done correctly. And we're going to continue here saying after the 2 solutions are combined in beaker 3, as described in part D, but before any reaction takes place, we're given a hydroxide ion concentration of 1.65 times 10 to the minus 4th molar. Using your answer to part D, calculate the value of the reaction quotient Q. Now, the reaction quotient Q is my ratio of products to reactants at any given moment, and Q can change. Now, we knew from part D, we had a magnesium ion concentration that we had calculated. Whatever answer you had in part D, you need to use here. So they're daisy chained together. And we were given in this problem a hydroxide ion concentration to use of 1.65 times 10 to the minus 4th molar. So if you're given that information, you're expected to use that in your calculation. We can substitute in the magnesium ion concentration, that our answer from part D, and we're going to use the hydroxide ion concentration that we were given here. We're going to substitute that in. I do want to point out that this is the reaction quotient Q, and Q of course can change. Don't call it K here because it's not the KSP, it's the current ratio of products to reactants, not the equilibrium ratio. We can substitute those values in. We do want to make sure we actually square that hydroxide ion concentration. We don't double it or anything. We just put it in just as it is because we're using the concentrations we have at that moment. And we get a value of 2.07 times 10 to the minus 11 for Q. So if you did all your calculations correctly and you're using your answer from part D and they match what they're supposed to be, this is what you had to do to earn 1 point. If you had made a mistake in your answer to part D but used it appropriately here in E part 2, you can still get credit for doing this part of the calculation, this part of the problem correctly. I do want to remind you that Q is dimensionless, so there should not be any units reported with Q. There is more to the problem, though. Using the reaction quotient Q, of course, that we just calculated, predict whether a precipitate should form as the mixture in beaker 3 approaches equilibrium. Justify your answer. So this is a Q versus K problem. You need to explicitly compare Q, which we just calculated, to the value of K, which we're given. Right? We know what K is. K won't change. And we have to use our answer from E part 2. So even if your answer from E part 2 is not correct, you can still earn credit for this for using the right approach and interpreting all your information correctly. What you need to remember with Q versus K problems, if Q is too big, if Q is bigger than K, that's saying that your ratio of products over reactants is too big. You have too many products and not enough reactants. And so I'm going to have to proceed in the reverse direction to make equilibrium. Do my comparison and Q is smaller than K, that tells me there are too many reactants. My ratio is too small. My denominator is too large and my numerator is too small, and I need to proceed in the forward direction to establish equilibrium. So if we look at the information that we have from our answer to E part 2 and the K that we were given, all right, we can see right away that Q is greater than K. The key here is to look at the exponents, all right? It's not the coefficients that matter initially. First, you want to look at the order of magnitude, and 10 to the minus 11 is a bigger number than 10 to the minus 12. Only if they're both the same, then you look at the coefficients, all right? And so in this situation, Q is greater than K, and therefore the system will proceed in the reverse direction. So yes, a precipitate would form. So really what you need to write here is Q is greater than K, yes, a precipitate forms. You don't actually have to go into more detail than that. That's what you needed to write to earn the point for E part 3. There's one more part to this problem. It feels like we've been doing it for a long time. In a separate experiment, the student adds nitric acid solution to decrease the pH of a saturated solution containing undissolved magnesium hydroxide solid. Does the amount of undissolved solid magnesium hydroxide increase, decrease, or remain the same as the nitric acid is added? Justify your answer. So let's think about the equilibrium system that we're dealing with here. We have magnesium hydroxide solid, and when you dissolve this in water, it makes tiny amounts of magnesium ions and tiny amounts of hydroxide ions, right? We know the KSP is very small. So this equilibrium system very much favors reactants, which are the solid. And we're going to add nitric acid. We're going to add a strong acid to it. We're adding a source of hydrogen ions. Well, hydrogen ions react with hydroxide ions to make water. So if we add nitric acid to this, it's going to react with the hydroxide ions on the product side and decrease their concentration. And if their concentration decreases, I'm going to end up proceeding in the forward direction to reestablish equilibrium. The hydrogen ions from the added acid are going to react with the hydroxide ions, and that's going to lower the hydroxide ion concentration in the solution. It's like I'm removing product. If I remove product, I'm going to make more product to reestablish equilibrium. Could also talk about this resulting in Q now being less than K, and therefore the system will proceed in the forward direction, and that's going to consume some of the solid magnesium hydroxide. But I do want to point out, notice how I led with the amount of the undissolved magnesium hydroxide will decrease. I answered the question. It asked, will it increase, decrease, or remain the same? You kind of want to lead with that, or at least put it at the top of your answer, even if you didn't write it first. And then you need to back it up. Okay, we're removing product. I'm going to proceed in the forward direction. That's going to leave me less mass of that magnesium hydroxide solid. And that's what you needed to talk about to earn the point for part F. I do want to point out, if you talked about the acid reacting with the undissolved magnesium hydroxide solid and making other things, that did not earn you credit. So how did you do? The average score on this question in 2025 was 4.78 out of 10. So 48%, just under 50%. So in some ways a very manageable question, but there were lots of places where it was easy to make mistakes. You want to make sure that you practice enough that you're not making those mistakes, because you can do this. You've been studying for a long time. You know a lot of chemistry. You want to show that off. If you found this helpful, like a video and leave a comment. And don't forget to subscribe to my channel so you get all my latest updates. Have a great day and keep studying chemistry.